Hello everyone, welcome to the fourth lecture of second week of our course on AI for art observation. In the last couple of lectures, we discussed support vector machine, how it works, some particular examples from the art observation domain, that is VMOS used. Specifically, we took the examples from before 2010. Eventually, we moved ahead and we briefly discussed about decision tree. And then we discussed a bit about underfitting, overfitting, and we said that decision tree is prone to overfitting. Here, with this background, we will be moving ahead to an interesting paradigm in machine learning, that is ensemble learning. Indeed, right now we will discuss ensemble learning in the context of decision trees. However, ensemble learning is also something very useful in the context of deep learnings as well. It's often used for uncertainty quantification and several other deep learning advanced paradigms. So with this, let us for now take forward our discussion based on the decision tree ensemble learning. Idea behind ensemble learning is that instead of trusting one model which might have overfitted, why not use many models such that each model makes its own prediction and then somehow combine all predictions by voting or some other mechanism. So this, in a way, we can call as the wisdom of crowds, right? Many moderately good models often outperform one excellent model. If you think about this, even outside the machine learning world, this is also something indeed very true in our practical life as well, right? Often when we go for an advice, we just don't go to, even though we know like the person in our friend circle who probably is wisest, we don't just go to that friend only, we rather go to a set of friends and we try to take kind of weights of those advices that we got from different friends, and accordingly we take our final decision. So this same wisdom of crowds, which we often use in our practical life, this is also something we are trying to use in this particular context. And here comes random forest, which is a collection of decision trees. So we said that a single decision tree, this might be overfitting on our training data. So that's why we are saying that why not take a collection of the decision trees. Very important point to note is that each tree is to be trained differently. So this again comes from the same idea, let's go back to our like going to the different friends and asking for advice. Think like this: each of your friends, they have a different view on life, right? They have gone through different experiences in their like upbringing. That's why when you are asking, posing them with a like a challenge that you need to solve in your life, they can come up with different perspectives, right? If it was the case instead, like all of them just saw exactly the same thing in their life, like exactly same things were happening from childhood. I mean, think of like a very synthetic example, like you picked up 5 persons, but somehow these 5 persons were from their childhood, like they were growing up in a like a locked house where they never saw outside of that house. They had like very few contacts except whatever happened in that house. In that case, most likely what will happen is that their experiences will be very similar, which might lead to, like them to just give you like the more or less similar advice. And then like you are not really benefiting from the wisdom of crowds, right? So this is the same thing we are trying to conceptualize here. That's why we're saying that okay, each tree has to be trained differently. And then we'll be combining the predictions from all the trees. So the randomness, as we see, like okay, in the name itself, there is random. So this randomness is coming from bootstrapped training samples. Additionally, so not just the training samples, additionally, random subset of features are taken at every split. So let us go into both of these particular terms that we have used right now, and let us try to understand them a bit more. Talking about bootstrapping, what does it mean? We randomly sample training examples. Sampling is generally done with replacement. Same sample thus may appear multiple times, and it may also be the case that some sample did not even appear. Now, the other important aspect is a random feature selection. At every split, randomly choose only a subset of features. Best split is searched only within that subset. So let's say you have 10 features, and it could always be the case. I mean, think of like, okay, you got a few job offers, okay? And there are like different aspects there, right? Like you have the salary, you have the location, you have, let's say, the different other kind of aspects like growth opportunity and all. Not sure how actually to quantify growth opportunity, but of course that's another aspect. So similarly, like maybe there are 10 different parameters, and if you like, like what can happen is that if you just try to take all those parameters together, it can often happen that your decision gets kind of embedded on just one of those features. Let's say the salary, you just like give so much importance to the salary, so like all the times you just decide based on the salary, and all the other features will just get ignored. So to ensure that this doesn't happen, you will actually need to, like sometimes think taking out the salary from consideration over completely. Okay, so this is the same thing happening here. Like at every split, we are not allowing all the features to appear such that like the dominating features, they don't always take the main role. Okay, so otherwise, I mean, even if like we are training different decision trees, they may end up just looking similar. So what happens with building one tree? For every tree, we create bootstrap samples and grow a decision tree such that at each node we randomly choose features and select the best split. So this is how like one particular tree is built. And then comes the forest. So this has two parts in the name, right? Random and then the forest. So this is the forest part where this particular process is repeated many times. And thus all these trees together, they form the forest. The prediction can be simply based on both. So let us try to understand a bit more. Why does random forest work? Random forest improves performance because decision trees, they make different mistakes. We have ensured, okay, they are like indeed like as different as possible, right? So they will like, the expectation is that they will make different mistakes, and averaging thus will reduce variance and thus will improve generalization. Random forest advantages include that it is resistant to overfitting. It handles nonlinear relationships. Usually, very little preprocessing is required, and robust, usually robust to noisy data. However, the limitations include that this is indeed now less interpretable than a single decision tree. One of the reasons we wanted to introduce decision tree was that this is quite interpretable, right? Now, with this new version of like where we are like at the bottom, we are still using decision trees. However, this new version of approach, that's random forest, is not anymore that much interpretable, I will say. I won't say that this is not interpretable at all, but not that much interpretable anymore. And the very large forests, that is too many decision trees, this obviously increase computation. So one obvious question that you would be probably asking is that why are we even interested in talking about decision tree or random forest? Before talking about SVM, we actually have convinced ourselves that indeed SVM was one very popular approach used in the pre-deep learning era. So the question automatically comes to our mind, is that also the case with random forest? And we see that indeed random forest used to be one of the popular approaches used in Earth observation. If you see the time bracket of like 2001 to 2010, And it's not the case again, like it's very similar to SVM. In fact, my own observation, I'm not giving you some empirical evidence here. My own observation is that, like, in some applications, specific applications, specifically, let's say, like when we work with atmospheric data and all, random forest is still quite popular, whereas SVM right now, like, is not used so much. So let us see a few examples to convince ourselves this better. So one example, again, like before the particular work, they are cited in the footnote. If you are curious, you can look them up. So this particular work is from 2006, where what is done is classification of a mountainous area in Colorado. 10 classes were considered. One class is water and the other are forest types. Landsat data, that is 4 spectral data channel from there. Additionally, other data channels such as elevation data, slope data, aspect data, they have been used in this particular use case. So we see like about 7 input features, right? One of the interesting things that can be done with a random forest and that has been done in this particular work is variable importance analysis. And after variable importance analysis, what they remarkably found is that the band 4, so we talked that there are like 4 bands from the Landsat, right? So the band 4 there, this is the most important band in this for this particular task we are talking about, followed by the band 2, again from Landsat, and then followed by the elevation data. One important point also to note is that this particular data set, as observed by the authors themselves, they had many outliers. Still, random forest performs satisfactorily, showing like how robust random forest is to the outliers. Random forest has also been adopted in several works related to hyperspectral image analysis. Even in the footnote, I have provided an example. This particular example is from 2005. Random forests are also quite robust to geographic variation. Random feature sampling and the ensemble learning, the core of the random forest, this indeed improves the model generalization to unseen areas better. With this, okay, so we started by talking about support vector machine. We then moved to decision tree, and on the top of decision tree we have built up random forest, right? So we'll be also talking a bit about unsupervised approaches such as clustering. However, before actually moving to like proper deep learning with the CNNs and all, let us talk about neural networks, which were also quite used in the era before 2010. And indeed, neural networks forms the basis of like our subsequent architectures that will be studying the CNNs and even vision transformers that we'll be studying later. So we let us study this neural network from both, like there are 2 different interests here. One is that some of the background will be indeed useful later to understand like CNNs and all, which actually forms the most of our course. The other thing is that, okay, the neural networks indeed, they were used to some extent before 2010, 2011, that particular era, right? So the epochs, the time epochs that we are talking about in this course is like this, like about mid 1990s to 2010, 2011 to let's say 2020, 2020 to let's say right now. Of course, actually, in the time that I gave you, it's a bit more from the computer vision perspective. If you think a bit more from Earth observation perspective, this time is slightly shifted because the CNNs and all in the Earth observation, they started getting adopted only slightly late, around 2014-15. Similarly, the vision transformers also got adopted a couple of years late, I will say. So we start by talking about perceptron. A simple perceptron accepts multiple inputs. It computes a weighted sum and it produces one output. So the perceptron, let us look a bit more visually. We see that let's say we have these inputs x1 up to xn minus 1, xn. So this all will be processed with these particular weights, let's say w1, wn minus 1, wn. Let's say we also have another w0 which gets multiplied with this constant 1. Now what's happening is that this we will be taking a sum here, and eventually we will process it using, in the case of the original perceptron we are talking about, we'll be just processing it using a step function and we will be getting the output. The problems that we generally deal with, they are not linearly separable, right? We already talked this particular aspect in the context of SVMs. So what we can do, we can go from perceptron, simple perceptron more towards MLP. And instead of just one neuron, what we can do is we can use many neurons in a particular layer, let's say several neurons, not just one neuron. Instead of one layer, what we can do again, we can use multiple layers. And this will take us from a simple decision paradigm to a complex decision paradigm. So one thing that we would like to mention at this point before moving forward is that the neurons, in this case we are considering, is slightly different from the version of the perceptron we just mentioned a couple of minutes back. How is it different? If you look at the picture, here we'll see clearly the main difference that we're talking about is in the terms of, instead of the step function, we are using some activation function. A couple of them we will be mentioning later. Thus, we have MLP, which consists of input layer, one or more hidden layers, output layer. Every neuron in one layer is visually connected to every neuron in the next layer. So this is very important aspect. This often we also call them as fully connected neural network. So this, how does it look then? Given the input, the first neuron we are seeing in the input, and in the hidden layer, let's say we have these 4 neurons and we have connected to this first neuron to all 4 of them, right? Similarly, this for the second and the third input, we did not show it, those connections, because the diagram would have become very jumbled, but you can imagine that those neurons are also connected. And eventually, then what we see is that there are two output neurons, let's say, and for each of these output neurons, again, from the hidden neurons, we see like the connections like between all of them. So we have input layer. The input layer simply receives features. So think again like of the mountainous area classification problem that we just discussed a few minutes back. How many input features did we have? If I remember well, didn't we have 7 of them? So now think like in this input layer, how many neurons we will be having to process like this input. Hidden layer, this essentially performs feature transformation. Each neuron learns useful patterns such as combination of the features. So the input features that we took, okay, so the combination of those 7 features, the nonlinear relationships, this will be learned eventually with the hidden layers. And more deeper you go, this discussion will be coming back again more in the context of CNNs. More deeper you go, you are learning more and more abstract features. Finally, we have output layer. If we are talking about binary classification, one neuron is sufficient. However, if we are instead talking about multi-class classification, in this case, we'll be using multiple neurons at this stage. Activation functions, they introduce nonlinearity, flexibility, expressive power. And I will just briefly mention this, and you can, if you're interested, you can of course study on your own. But this will again come back when you talk in the context of deep learning CNNs. So sigmoid activation is one popular activation used. And similarly, another one that is used is ReLU activation, which is quite simple, as you can see in the equation. It's quite simple and most widely used in the context of CNNs at least. Now, let us think a bit about how the learning happens in MLP. And this is more or less the same now forward when we'll be talking CNNs and vision transformers. The training cycle involves forward propagation, loss computation, back propagation, and weight updating, and this process is repeated. The back propagation, which computes gradients and adjusts weights to reduce future prediction errors. Let us go back a bit again to the overfitting. We said that large networks are prone to, more complex, we rather say like more complex networks, they are prone to overfitting. So in this case, think like what does the complexity straightforward translates to? Doesn't it translates to like how large the network is? So the large, if you just take large network without support of training data and all, or some kind of regularization, which we'll also mention soon, it may end up that, okay, you are just overfitting, you are just memorizing training data. That's why with neural network, we often use regularization techniques. So many of these regularization techniques that I mentioned here, they got popularized only when CNN was introduced. However, I'm mentioning it in a bit more general way here already. So one, of course, is like using more training data, as we have already discussed, that how training data is important and how training data, more and more training data pushed forward the revolution of development of more of like larger and larger architectures. Data augmentation is another possible regularization technique. So these two, training data and data augmentation, these are of course more in the data world, whereas you can also do more in the the network itself or like the training strategy itself. So there comes dropout, one possibility, early stopping, one possibility, L2 regularization, one possibility. The number of layers, initial weights, the type of activation function, and the details of learning process, this all can be treated as parameter, and they are often tuned to improve the performance of a neural network. So here it's important to also differentiate a bit between when in this context, in the neural network context, we say model parameter, we generally imply the learnable internal values of the neural network. During training, the learning algorithm estimates these parameters from the training data and the learning mechanism. Whereas when we talk about hyperparameters, they are these external parameters which are set by the operator or the user of the neural network. With this, let us stop here. We'll take forward our discussion to unsupervised clustering and a bit about change detection in the next lecture. Thank you.